In the last lecture, we had looked at the Planck blackbody radiation. And we saw that the Planck blackbody formula for emissive power was 2 pi h nu cube by c squared e to the power h nu by k t minus 1, where h is the Planck's constant, k is the Boltzmann's constant, and c is the speed of light in the medium. Now, this formula for the emissive power can be derived using principles in statistical mechanics and quantum mechanics, but we went through another approach which was proposed by Einstein, and which is much simpler to understand and highlights clearly how these two terms in this equation, how this term and this term appear in this equation. And to do that, we went through Einstein's derivation, and we saw that we had upper level I and lower level j, and we wrote down three expressions. One is dni dt equal to minus aij ni for spontaneous emission, and then we had dni change in number of molecules in time due to induced emission, which is the new idea that Einstein had. He said that there can also be emission of photons due to photons coming into the system. So, that is induced emission or spontaneous or stimulated emission. And finally, there is absorption, which has to be positive and which is from lower level j to upper level I. So, it depends on number of molecules in the lower level and the number of photons arriving at the system. Now, Einstein assumed that the incoming radiation is from black body and isotropic in all direction, and so he wrote down integral of I nu d nu as nothing but integral I nu b into 4 pi. So, this is because the radiation is coming isotropically in all direction, and then in equilibrium the sum of these three terms has to be equal to 0. So, we are going to assert that dni dt spontaneous emission plus dni dt in induced emission plus dNi dt absorption is equal to 0, because in steady state all the number of molecules any level does not change. So, if we do this calculation, we will find simplification of that formula Ni into Aij plus I prime nu b into 4 pi into Bij is equal to Nj Bji 4 pi I prime nu b. Okay. And the by the arguments related to symmetry and reciprocity, Einstein assumed that Bij must be equal to Bji. The process of emission absorption have to be symmetric and reciprocal. And then we assume that the number of molecules at the upper level to that in the lower level has to go as e to the power of minus delta E by kT, which is equal to e to the power of minus h nu by kT. So, we are assuming that the molecules have a distribution following the well known distribution that comes from statistical mechanics, that the distribution of molecule has to decrease exponentially with height. And now, if you put all this together, you will get I prime nu b as Aij by Bij divided by 4 pi e to the power of h nu by kT minus 1. So, the beauty of this result, now if you want to get a result which is same as what we derived for the Planck's formula, we know that E nu b is equal to pi times I prime nu b. Therefore, you can write E nu b from Einstein's derivation as Aij by Bij divided by 4 e to the power of h nu by kT minus 1. And we do not know right now what this ratio is like, but if you compare this result with the derivation done by Rayleigh and Jeans in the classical limit, one can show that Aij by Bij is nothing but 8 pi h nu cube by c squared. And so, we get back the result that is obtained by Planck, but the advantage of this derivation is that it clearly shows that this 1 comes from induced emission, which was not accounted for by either Rayleigh and Jeans or by Wien in his derivation. So, this is the term which was introduced by Planck, but Planck introduced it somewhat ad hoc fashion, while in Einstein derivation this comes out very naturally as a contribution of induced emission to the result. So, this derivation provides insight regarding the terms, and this shows that this term is coming from the distribution of molecules showing a decline with energy levels. So, both these are clearly accounted for in this derivation. Now, this derivation done both by Einstein and Planck use the frequency coordinate system, that is, we calculate emissive power per unit frequency but we also would like to know what is the value per unit wavelength, and that, as you recall, can be easily obtained from this equation. So, once you know B from here, and you know what is d nu b, because we know that nu into lambda is c, we know that d nu by d lambda is minus c by lambda squared. Okay. So, if you count this and convert all this frequency to wavelength, we get an expression for E lambda b, which is fairly well known. So, E lambda b becomes 2 pi h c squared lambda to the power of 5 e to the power of h c by lambda k t minus 1. So, this is an expression that is used very often. This expression has interesting properties. One is that if you divide E lambda b by t to the power of 5, the right hand side is only a function of the product lambda t, and this is very useful. Later we will see that we will exploit this particular feature of this function to our advantage. The next important issue to know is that where is the maxima of the Blackbody function, and that you can obtain by differentiating this equation, and you will get a transcendental equation which you have to solve numerically, and if you do that you will get the following result. The wavelength at which it is the maximum will come out as 2898 by T, where T is in degrees Kelvin. This answer is in microns. So, this says that the peak of the Blackbody emission curve, when you look at the emissive power per unit wavelength, occurs at this wavelength. On the other hand, if you look at the previous derivation with respect per unit frequency and find out what is the maximum frequency, and then from there get the wavelength, you will get that this will maximize at a wavelength given by 5077 by T micron. So, what this means is that the maxima of the E lambda b function occurs at a different wavelength than the maxima of the E nu b function. This is not surprising, because you recall that the E lambda b function goes as 1 over lambda to the power of 5, while the E lambda b goes as 1 over lambda to the power of 5, while E nu b goes as nu cube. So, these are different kinds of functional dependence. So, the maxima of these two functions will not occur in the same wavelength. So, when you quote the maxima of any Blackbody function, it is important to mention which coordinate system you are working at, but most books quote the value that is given by E lambda b function, and this is called the Wien's displacement law. Okay. And this is very useful information as to where exactly the peak of the Blackbody function lies. Now, another quantity of great interest to us, in addition to the peak of the Blackbody spectrum, is also the total amount of radiation lying. Now, before we go there, let us look at a typical Blackbody at the temperature of 289.8 Kelvin. Then you find its maximum radiation at in the E lambda b coordinate will occur at 10 micron. So, what it means is that if you look at bodies at room temperature and if they behave like black bodies, then their peak radiation occurs around 10 micron, and this is true of most objects at room temperature. So, their maximum emission occurs in a region around 10 microns. On the other hand, if you look at the sun's emission, assume sun is a black body at 5796 Kelvin for convenience, then you will find that the maximum radiation occurs at 0.5 micron. So, you can see that there is a huge difference where the maximum radiation lies. For bodies around room temperature, the peak is around 10 micron, while for bodies such as sun, which is at high temperature, the maximum is around 0.5 micron. And this information will be very useful when you want to determine the amount of radiation absorbed from the sun, for example. Then it means that you need to have a surface which absorbs radiation very effectively in this region around the visible. So, this issue we will take up again a little later. In addition to the where the maxima lies, we also would like to know how much energy lies in a certain wavelength range. So, we will like to know the following quantity: what fraction of radiation from a black body lies in the, let me just write down this expression. So, you look at the total radiation emitted by a black body and then compare with how much radiation lies in a given wavelength range. So, this tells you what fraction of the radiation emitted by a black body lies in a certain wavelength range. This is a very important information, and to do that this kind of analysis, we first have to know what this quantity 0 to infinity E lambda b d lambda, or it can also be 0 to infinity E nu b d nu. What is this quantity? Now, this quantity leads us to the well known Stefan-Boltzmann's formula. Let me do a quick derivation of this. So, E b, which is the total radiation lying in all frequency of wavelength. So, we use the Planck's expression. Now, this derivation is quite easily done if you assume a non-dimensional parameter eta, which is h nu by k t, okay, and then you write your E b as 2 pi will come out, h will come out, and c square will come out. You have 0 to infinity, you will have now multiply up and down by k cubed d cubed by h cubed to get eta cubed, e to the power eta minus 1. Then you want to do d eta there. So, multiply by another k t by h. Then you get the expression E b is equal to 2 pi, 1 h will go out here, h cube c squared e to the power of 4 t to the power of 4 0 to infinity eta cubed e to the power of eta minus 1 d eta. Now, this integral that is given here is just a number. So, right now we may not worry too much about what the number is, but we are more interested in knowing what is the dependence of the emissive power and temperature. That comes out as T to the power 4. So, if you evaluate this integral, this comes out as y to the power 4 by 15. This kind of integral is studied in when you study complex numbers. You find the poles and zeros of this function and then evaluate the integral, or today you can just use either MATLAB or Mathematica and get this number. So, if you do that, you will have a simple expression E b equal to 2 pi to the power of 5 by 15 k to the power of 4 by h cube c squared into t to the power of 4, and this quantity is called the Stefan Boltzmann constant. And the numerical value of this quantity had been derived even before Planck had made his derivation for the spectral quantity, because in the laboratory you can measure E b as well as T, and after that you obtain this quantity empirically. But today we know this quantity called Stefan Boltzmann constant with the symbol sigma. This quantity can be evaluated from 3 of the universal constants in physics: the Planck's constant, the Boltzmann's constant, and the speed of light in vacuum, because this blackbody radiation is for calculation for vacuum. So, if we finally write E b equals sigma t to the power of 4, and this quantity can be remembered very easily. So, this quantity is 5.67 10 to the power of minus 8 watts per meter square kilometer power of 4, and this is such a easy number 5678 that you should never forget it in your lifetime, because it is worth remembering very easily. So, now having done this, now we go back to our expression, how much radiation lies between two wavelength. We can write this as lambda 1 to lambda 2 E lambda b d lambda. In the denominator was 0 to infinity, that comes out now as sigma t to the power of 4. Now, this can be simplified a little bit if by writing this as lambda 1 t to lambda 2 t e to the power of lambda by sigma t to the power of 5 d lambda t. Now, it is useful to write this expression this way, because if you look at the expression for E lambda b, we had already pointed out that E lambda b by t to the power of 5 is a function only of lambda t, and therefore, our expression for radiation lying between two wavelengths essentially becomes lambda 1 t to lambda 2 t f lambda t by sigma d lambda t. So, we need to know lambda and t together in order to calculate this value. You can also write, based on the simpler way of writing this, f 0 to lambda t can also be written as 0 to lambda t f lambda t by sigma d lambda t. Okay. So, this expression is useful to evaluate numerically today using MATLAB or any other standard integration procedure, and I will give you some simple values which are useful to know. Suppose you are looking at lambda t value and what fraction of radiation lies between 0 and that lambda t, then the important ones are at 1448 micron Kelvin you will have 0.01, at 2898 it will be 0.25, at 4108 it is 0.5, at 6149 it is 0.75, and at 23,220 it is 0.99. So, this is a useful table to have. What it means is that most of the radiation emitted by a black body lies between, that is 98% of the radiation lies between 1448 micron Kelvin and 23200 micron Kelvin. So, in evaluating property surfaces, this information is useful because you need to know in which wavelength range the radiation primarily lies. So, let us take a few examples to illustrate that. Let us take a surface at 300 Kelvin. So, 98% of the radiation lies between 1 between 1448 by 300, which is nothing but approximately 4.81 to 23220 by 300, which is approximately 77 micron. So, one can say that most of the radiation is emitted by a black body at 300 Kelvin is somewhere between 4 micron to 75 micron. On the other hand, if the temperature of the object is closer to 6000 Kelvin, okay, this is closer to room temperature, this is closer to sun's temperature. So, 98% of the radiation lies between which is around 0.24 micron to 23220 by 6000, which is approximately 4 micron, very close to 4 micron. So, we can say with some confidence that most of the radiation emitted by a black body 6000 lies between 0.25 and 4, while most of the radiation from a black body around room temperature lies between 4.8 micron and 77 micron. So, what is interesting is that what this shows is that the two are almost non-overlapping. So, the sun's radiation lies between 0.24 and 4, while this is somewhere between 4.8 and 77. So, the radiation emitted by the sun and a body at room temperature do not have much overlap. They are completely non-overlapping wavelength domains, and this becomes very useful to know when you want to evaluate properties of surfaces the properties are relevant to calculating the absorption of sun's radiation will be very different from the properties that you will have to use to calculate the emission by the surface, because the two wavelength domains are completely non-overlapping in their character. Now, so this information is interesting. The second information is interesting is we saw that E lambda b by d lambda was 0, where lambda t was 2898 micron Kelvin. We also see that 0 to 2898 E lambda b d lambda by sigma t to the power of 4 is 0.25. So, what this means is that if you plot E lambda b with lambda, then 25% of the radiation so 25% lies before the maxima and 75% lies above the maxima. What this implies is that the Blackbody function has a long tail. It is not symmetric like a Gaussian distribution, it is asymmetric. So, to the left of the maxima there is only 25% of the radiation, while to the right of the maxima 75% of the radiation is there. So, this feature is to be remembered when you are doing calculation, that the functions are not symmetric as you would have assumed. Okay. So, this is the properties of a black body, but remember that we are dealing with real surfaces, not black bodies. So, we need to now look at the properties of real surfaces and then compare this real surface with a black body. So, one important property we should remember is that black body is the best emitter and the best absorber. So, when you compare a real surface with an ideal surface like the black body, both at the same temperature, the emission by a real surface will always be lower than that of the black body at the same temperature. So, this gives us a chance to define what is called emissivity. So, now we talk about properties of real surfaces. So, real surfaces are different from ideal surfaces. So, the first important property that we will talk about is emissivity. So, emissivity compares the emission of a real surface to that of a black body at the same temperature. For example, the directional spectral emissivity of a surface is the emission in a given direction, given wavelength by the actual surface to that of the black body at the same temperature. So, this is a very fundamental definition of what is directional spectral emissivity. Similarly, we can define directional spectral absorptivity, but in this case we define the directional spectral absorptivity as the amount of radiation absorbed in a given direction, given wavelength, to the radiation incident in the same direction and same wavelength. So, I want you to notice the difference between emissivity and absorptivity. Emissivity is defined as a ratio of the actual emission to the blackbody emission, while absorptivity is defined as a ratio of radiation absorbed to the radiation incident. Okay. So, so there is a fundamental difference between these two definitions, but remember at the microscopic level emission absorption are what is called reversible. That is, if a certain object had a certain probability of absorption, the same object will have similar probability to emit radiation, because when there is emission, molecules fall from the upper state to lower state and emit a photon. If you send the photon back, then there is an equal probability that the molecule will absorb the radiation and take the molecule from the lower state to the upper state. So, Kirchhoff proposed that under most conditions these two quantities are equal. The only requirement that he imposed on the equality of directional spectral absorptivity and directional spectral emissivity is that the object must be in local thermodynamic equilibrium. So, in local thermodynamic equilibrium, the ability of an object to absorb radiation at one wavelength and one angle will be same as the ability of that object to emit radiation at the same angle and same wavelength. Now, I want to warn you that Kirchhoff's law only relates the directional spectral quantities. Although this is always true, you must remember that the hemispherical spectral absorptivity is not always equal to hemispherical spectral emissivity. Similarly, directional total absorptivity is not always equal to directional total emissivity, or the hemispherical total absorptivity is not equal to So, these three things you must remember, because many books claim that this Kirchhoff law or this is Kirchhoff's law. It is not true. Kirchhoff law only connects the most basic quantity, that is the directional spectral quantity between absorption and emission. It does not say anything about quantities which are obtained by averaging. Once you average absorption and emission, then things change substantially. And so, I want to illustrate as to why, for example, alpha prime will not be equal to epsilon prime. So, let us now go through the derivation to understand why this is true. What is epsilon prime? By definition, it is the directional total emission by the object at a given temperature by the directional total emission by a black body at the same temperature. And this can be defined as as follows. So, what you see that we obtain the directional total emissivity from the directional spectral emissivity by weighting the directional spectral emissivity by the blackbody function at the temperature of the surface which emits radiation. On the other hand, we define the directional total absorptivity as the total radiation absorbed at that angle by the total radiation incident at that angle. And notice that the directional total absorptivity does not make any reference to any blackbody function. So, if you write this in terms of intensity, you can write this as 0 to infinity while the denominator is this from the definition of intensity. Okay. Now, you see there is a very basic difference between this integration and this integration. When I am integrating the directional spectral emissivity, my weighting function is that of the blackbody at the temperature of the surface, while when I am integrating the directional spectral absorptivity, I am integrating with the amount of radiation incident on that object from some source, which may not be a blackbody. So, this clearly shows that absorptivity that you obtain for any substance depends very much upon what is incident on that surface. So, if sunlight is incident on surface, its absorptivity will be one value, while if radiation from some other source is incident on the surface, it will have a different value. So, alpha prime will differ substantially from one situation to another because the incident radiation is different. Now, to compare these two and see when can you apply Kirchhoff's law for this kind of situation, I will first write epsilon prime 0 to infinity epsilon prime lambda I prime lambda b d lambda by 0 to infinity I prime lambda b d lambda, and alpha prime as 0 to infinity, then using Kirchhoff's law epsilon prime lambda I prime lambda I d lambda So, now these two look somewhat similar, but not same, because in the case of emissivity you are weighting it with the blackbody intensity at the temperature of the surface, while in the case of absorptivity you are weighting it with incoming radiation intensity and its distribution with wavelength. But we can see that if by chance the incoming radiation happens to be proportional to the blackbody intensity at the surface temperature, then we can say these two are equal. But in real world this will be very rare. It will be a rare occasion when the radiation incident on a surface has a wavelength distribution proportional to that of the blackbody at surface temperature. So, this is going to be satisfied very rarely. Okay. The other case is by chance if this quantity is not a function of lambda, is independent value, you can take this out of the integration, then both these are equal, and so this is what is called a gray surface. So, you see that we can assume the directional total absorptivity to be equal to directional total emissivity if, so we will have to write down clearly in the next page. So, I will say that this is equal if A surface is gray or B incoming radiation is proportional to blackbody radiation at the temperature of the surface. Both these occur very rarely. Most surfaces that we encounter have strong valence dependence of absorptivity or emissivity, and hence an assumption of a gray surface is not very accurate. Secondly, it is a rare occasion when the radiation coming on object happens to be having a valence dependence which is following that of the blackbody at the temperature surface. So, I would say that this is not very useful information to have, but we are highlighting it because there are many books we call this equality as Kirchhoff's law. That is not true. Kirchhoff's law only depicts the relation between absorptivity and emissivity for directional spectral quantities and not for directional total quantity. So, the validity of this is very specialized, either gray surface or the incoming radiation proportional blackbody intensity at the temperature surface, which is rarely satisfied in the real world. So, neither condition is met in the real world, and hence these two are not equal. So, it is a rare situation that this is really satisfied. Now, let us look at the other question. Suppose instead of integrating over wavelength, you integrate over angle. Let us ask, when is this equal to this? When is the hemispherical spectral emissivity equal to hemispherical spectral absorptivity? To do that, once more we go from basic definitions. We define this as E lambda of T s by E lambda B of T s, that is 0 to integral over omega of epsilon prime lambda E prime lambda B d omega divided by E prime lambda B d omega. So, we are obtaining an hemispherical quantity by averaging over angle. So, just to remind you, we start with the basic quantity, that is spectral. Last time we did the valence integration, we got this quantity. Now, we are doing angular integration and getting this quantity. We can reverse it later if we want. Ultimately, we will get epsilon, which is the total hemispherical emissivity. Now, remembering the fact that E prime lambda B is nothing but I prime lambda B cos theta from basic definition of intensity emissivity, and the fact that I prime lambda B is not a function of theta and phi, both these we know. So, both this information we can write down epsilon lambda as integral over omega epsilon prime lambda I prime lambda b d omega. At the bottom, integral I prime lambda b d omega. Now, remember that the definition of intensity is such that we know that the directional spectral emissivity of black body is not a function of angle. That was built into the definition. So, both these integrals come out, and I am sorry, I forgot a cos theta there. There is a cos theta here. So, if you do the integration, this will come out as pi. Okay. So, final expression for epsilon lambda we are getting is 1 over pi integral over omega e prime lambda cos theta d omega. And the main lesson you have to learn from this expression is that we do not obtain hemispherical value by merely taking the directional value and averaging it over arithmetically. We have to weight it with cos theta. So, cos theta weighting is important, which means that more weightage is given to emission closer to the normal so this region will have higher weightage than this region. So, this is worth remembering that the directional quantity when it is integrated, there is a cos theta term there, which ensures that more weightage is given to radiations appearing at emitted at lower values of theta. So, now we move on to absorptivity. The hemispherical spectral absorptivity is defined as integral omega alpha prime lambda I prime lambda I d omega divided by I put a cos theta there. Now, this comes from the basic definition of absorptivity. This is the radiation incident in the solid angle and what fraction is absorbed. This is radiation incident in the same solid angle. Now, if you assume Kirchhoff's law, which is always valid, then we have alpha lambda is equal to now let us compare the two expressions for emissivity and absorptivity. We saw epsilon lambda is 1 over pi integral over omega epsilon pi lambda cos theta d omega. while alpha lambda is somewhat different. So, you can see that in general these two are equal if 1 epsilon prime lambda is not a function of angle. That is, the emissivity surface emits diffusely and isotropically. And other possibility is, or the incoming radiation is not a function of theta and phi. So, the incoming radiation is emitted equally in all direction, then also this integration becomes. So, in one case we take this out into an infinite angle and take this out, or we take this quantity out. So, to conclude, in this lecture we have focused on properties of blackbody radiation and the properties of real surfaces. We define emissivity and absorptivity at its most basic level, and then we invoke Kirchhoff's law, which says that the directional spectral emissivity equals directional spectral absorptivity. Then we went on to show under what condition you can assume equality between hemispherical spectral emissivity and hemispherical absorptivity, and we saw that they are only equal under very special conditions. We will continue this discussion further, because there is a lot of misunderstanding about how to invoke Kirchhoff's law. So, we will spend some more time highlighting the misuse of Kirchhoff's law.